We have a regression model. Y is just a character. X is just a symbol. It can mean anything I want it to do. X could be exactly that, a single variable. X could be a matrix. And there could be anything in it that I wanted. I'm just using it as a symbol or a placeholder. I'm using Y as a symbol or a placeholder. There's nothing special about the choice of Y. And then I say things like, the rank of the matrix of observations on X is K. It's a full column rank. And then I say, the expected value of X transpose U is 0. So the correlation between the independent variables and the error is 0. And then I say something like the expected value of U is column vector of zeros. And I say further that the expected value of U transpose is equal to sigma squared I. Does my assumption about the expected value of UU transpose imply anything about the structure of Y is equal to X beta? No. It's a completely different discussion. The Y, the X beta part, that's the non-stochastic part of my model. Although it turns out that's not the critical assumption. The Y and the X and the beta part is non-stochastic. Oh, let me put one more thing here. Model is correct, as stated. For the moment. So my discussion of the structure of the expected value of UU transpose is irrelevant to how I specified the X beta part of my model. Now the X beta part, the X, that could have current X's in it, it could have lagged X's, it could have lagged Y's in it. Anything that I want could be in it. And for most of the time in class, it didn't much matter what was in it. When I think about the first assumption, that X is a full column rank, does that have anything to do with the behavior of the error term? Nothing at all. So any issue involving the content of X is irrelevant to the structure of the error covariance matrix, except, of course, if I have violated this assumption. So at one time or another, we've considered different violations. Violating this one is a question of multicollinearity. And most of the discussion in the literature is very rough and ready. Because as a statistical matter, there's not much that we can say about testing for multicollinearity. In large part because the cause everybody knows from basic statistics and when they were first introduced to regression analysis that a rough and ready test, a rough and ready indication that there is multicollinearity is that if you have a significant F statistic for the model, but you have no significant T statistics. How did that happen? Well, it happened because some of the right-hand side variables were linear combinations of the others. When that happens, the coefficient covariance matrix gets very large. So none of your T statistics are significantly different from 0. But as a group, they do a great job explaining the variation in Y. And so you get a big F. The presence of multicollinearity comes from two places. One is the variation within an independent variable. And the other is from the magnitude of the characteristic roots of X transpose X. One of the things that you can show algebraically, and it makes them intuitive. When we geometrically look at multicollinearity, we look at the variation within an independent variable, and we look at the size of the characteristic root of X transpose X that corresponds to that independent variable. And it's the ratio of those two that, in fact, determines whether or not multicollinearity is a problem. You'll see in a bunch of different places, and it's discussed in green, this notion of something called a variance inflation factor. And in fact, JJ sent me something today where the author of this piece that he gave me was relying on the variance inflation factor. The variance inflation factor is not a test statistic. If it's big, that's a bad thing, but how big is big? We don't know. So mostly, multicollinearity is a question of judgment. In economic data, you can be sure that multicollinearity is a problem. And in detecting it, people look at things like simple correlations between the right-hand side variables. Or they look at the test statistics they got, the key statistics that they got for the individual coefficients and the overall F for the model. And that tells them something. What do you do about multicollinearity? Well, given our original assumption that the right-hand side variables are fixed in repeated samples of size n, well, apparently, either we made a mistake in the specification of the model, or maybe the x's are stochastic, and we just happen to get an unfortunate sample. If we could go out and collect another sample or more data, the multicollinearity problem would go away. But the whole issue of whether or not you have multicollinearity and what you're prepared to do about it is a judgment call. Although there is somebody in here who asked me about principal components. So this could be a problem. That's multicollinearity. It's what might be called a pathological disease. Of course, the model is correct. That's what hypothesis testing is all about. The very details of how we do hypothesis testing change as we encounter some of these problems. Whether or not the mean of the disturbance is 0 is irrelevant. If it's not, the intercept just changes. It doesn't change anything else. There's no adverse consequences. So we don't even need to worry about that. Suppose that a right-hand side variable is correlated with the error term. Well, we didn't talk about that this semester. Suffice it to say that it's a bad thing because it means that our ordinary least squares estimators are no longer consistent. Consistency hinges on the independence of the x's and the u's. When are we going to talk about that? Well, in the spring, we would talk about that, or you will talk about it, I hope, with Professor Uders, if you take Econometrics II. So we didn't really talk a great deal about this.